Okay, hello everyone. My name is Shelta Molidia from Fluid Mechanics class 03. So here I want to present to you all a review of my final exam. So the content here is the I5 question, question number 1, number 2, number 3, number 4, and number 5. So the I5, like we already know, the I5 concept has 4 steps, which is the intention, initial thinking, idealization, and instruction. So the intention is basically the understanding of the primary goal of the problem. So initial thinking is gather all the given data and relevant information provided in the problem and creating a free body diagram. The idealization is make necessary assumption and simplify the problem so we can easily solve it. And the last step is the instruction, which is the outlining a detailed step-by-step plan for solving the problem. So next. So this question below are the final semester exam question in fluid mechanics course. So the question number 1 is about flow through an orifice metal. Question number 2 is about spray heads and pipes diameter. Number 3 is about the declaration of an automobile by a direct parachute. Number 4 is about flow in open channel. And the last one, number 5, is choke flow in a converging nozzle. So question number 1, an airflow rate up to 1 meter cubic per second at standard condition is expected in a 0.25 meter diameter dutch. And a revised meter is used to measure the rate of flow. So the manometer available to make a measurement has a maximum range of 30 100 millimeter of water. Determine the diameter of the orifice plate that should be used with D and D per 2 pulsar taps. And determine the head loss if the flow rate at the vena contracta is 0.65 of the orifice diameter. So the intention of this problem is to understand how to determine the head loss if the flow area of the vena contracta is 0.65 of the orifice meter. And here I forget to write it, which is the determine the diameter of the orifice plate. And also, of course, the last but not least is we have to set the intention for we learn it for God, or for Allah and Islam. So next one is the initial thinking. So the initial thinking of this problem is So the initial thinking is Q equal to 1 meter cubic per second, deduct equal to 0.25 meter, next range is 300 millimeter, and the area of vena contracta is 0.65 of the orifice diameter, which is, we can also write it the area of vena contracta is 0.65 times area of orifice metal. Here is the free body diagram that I draw. Next, the idealization. So the idealization of this problem is we assume that this system is steady state and the flow is incompressible. The flow of water is 1000 kilogram per meter quadrat. The gravity is 9.81 meter per second quadrat, and discharge coefficient is 0.65. So discharge coefficient range is about 0.6 till 0.65, and we assume that the discharge coefficient we use is 0.65. So the instruction is, first we have to find the delta pressure with the equation of delta pressure equal to rho times G times H. We input the number, and we get the delta pressure is 2,943 Pascal. So we input this delta pressure to the first equation, which is Q equal to CD times A0 times root 2 times delta P per rho, and we rearrange so the equation, we change the A of orifice matter here to P times D quadrat per 4, and we rearrange the equation, and we get D quadrat equal to 4Q per P times CD times root 2 times delta P per rho. So we get the D approximately about 0.89 meter. After we find the D, we can find the head loss using the equation head loss equal to delta P open bracket 1 minus AV per AO. AV is area of vena contracta, and AO is area of orifice matter, close bracket quadrat. So we input the number, and we get the head loss is 360.51 Pascal. So for question number 2, it is spray heads in an agricultural spraying system are to be supplied with water through 500 feet of ground aluminum tubing from an engine-driven pump. In its most efficient operating range, the pump output is 1,500 GPM or gallon per minute at a discharge pressure not exceeding 65 psig. So for satisfactory operation, the sprinklers must operate at 30 psig or higher pressure. So it can be lower than 30 psig. So the minor losses and elevation change may be neglected to determine the smallest standard pipe size that can be used. So the intention is to understand how to determine the smallest standard pipe size that can be used, and also to ask God to guide us, to help us to solve this equation and to understand it. So the initial thinking, here we get the free body diagram and the data that the equation provide us is Q equal to 1,500 GPM. We convert to CFS and we get 3.34 CFS. So the length of the pipe is 500 feet. The pressure max or P1 or pressure at discharge of the pump is 65 psig, and the P2 or P min is 30 psig. So here we use the Darcy-Weisbach equation, which is head loss or HL equal to F times L per D times V quadrat per 2 times G. And we also use the continuity equation, which is Q equal to A times V. So the idealization is, we assume that this system is steady state and the flow is incompressible flow. So the negligible minor losses, which is HF equal to H pump, and number 4 is V1 equal to V2 equal to V. And the instruction is, first we have to find the delta pressure. We use the equation like pressure max minus pressure mean, and we get the pressure is 335 psig. So after that we convert the delta pressure to feet, and we get 18.85 feet. So after that we use an try and error method to find the smallest standard pipe, because so here I try with a 4-inch diameter pipe, and if we convert to feet, it is approximately like 0.333 feet. So we enter this to the equation. The equation is A equal to P times D quadrat per 4, and we get the A is 0.087 feet quadrat. After we get the A, we input this number to the V equation, which is V equal to Q per A, and get the V is 38.3 feet per second. And the second guess is I use 6-inch pipe, which is like 0.5 feet. So we input it to the equation and get the A is 0.196 feet quadrat, and the V is 70 feet per second. So to find the head loss of this two type of pipe, we have to know the F or friction, and I assume that the friction for turbulent flow is approximately like 0.02, and so we just get it, we just go with it. And so here for the 4-inch pipe, the head loss is F times L by D times V quadrat by 2 times G, and we get 273 feet per. And for the 6-inch diameter pipe, we get the head loss is 22.4 feet. So the conclusion is the 4-inch pipe has the head loss of 273 feet, which is exceeding the allowable pressure drop. The allowable pressure drop is the 80.85 feet, and the 6-inch pipe, which has the head loss 22.4, is within the allowable pressure drop. So we can use the 6-inch pipe for this problem. So next is problem number 3. A dragster weighing 1060 lbf attained a speed of 270 mph in the quarter mile. Immediately after passing through the timing light, the driver opened the drag chute of area 25 feet quadrat. So the air and cooling resistance of the car may be neglected. Find the time required for the machine to decelerate to 100 mph in standard air. So the intention is to understand how to find the time required for the machine to decelerate to 100 mph in standard air. Here we have the initial thinking. So the initial thinking of this problem is V0 is 270 mph, the Vf is 100 mph, the W is 1600 lbf, the area is 25 feet quadrat, and the gravity, it is actually the acceleration of the gravity, which is 32.2 feet per second quadrat. So at this problem we use Dragfors equation, which is Fd equal to 1/2 times rho times Cd times A times V quadrat, and we also use the second law of Newton, which is F equal to m times A equal to minus Fd. So next, the idealization is that V0 equal to 270 mph, and we convert to feet per second and get 396, and for the Fv we get 100 mph and convert and get to feet per second and get 146.67. So we also assume that the rho of the air is 0.00277 slugs per feet quadrat. It is standard air density at sea level actually, and the CD is 1.5. It is I assume it based on typical value of circuit. So next is instruction. So first we have to find the m with the equation of W equal to m times g. We input the number, we rearrange the equation, and it becomes m equal to W per g. We input the number and get the m is 49.69 slug. So after that we want to find the t with the motion equation, which is ma equal to minus 1/2 times rho times Cd times A times V quadrat. So we rearrange the equation and it becomes A equal to minus 1/2 times rho times Cd per A times Cd per times A times V quadrat per m. So after that we get the integral. So integral V1 V0 dv per V quadrat equal to minus 1/2 rho times Cd times A per m integral V 0 dt. So we get open bracket minus 1 per V close bracket, Vf and V0 equal to minus 1/2 rho times Cd times A per m integral T 0 T. So actually I used the scientific calculator to solve this problem, but here I write a little bit of step by step how to calculate it. But at the end we get the T is 4.828 seconds. So next is, here we get the image of the absolute coordinate and coordinates at s relative to wave. So the equation is we have to find the motion of surface wave. So the intention is to understand how to calculate motion of surface wave. If we want to calculate the motion of a surface wave, we have three we have three what? Oh, what does it mean, cara? Tiga cara. I forgot what does it mean, cara. So yeah, back to this. So the first one is wave in deep water. So for the wave in deep water, in water greater than water greater than half of the wavelength, the sea wave speed v can be calculated by the following formula, which is v equal to root g times lambda per 2p. The second one is wave in shallow water. For the wave in shallow water, which is the water less than 1/12 of the wavelength, the wave speed can be calculated by the following formula, which is v equal to root g times h. And the last one is wave at intermediate depth. So for the wave intermediate depth, where the water depth is between the boundary of deep and shallow water, the calculation may be complex and often use numerical approach or empirical tables. So to calculate the speed of propagation of ocean wave, it is necessary to know the wavelength and water depth. The formula used will differ based depending on whether the waves are in shallow or deep water. So in shallow water, the wave speed depends on the water depth, while in deep water, the wave speed depends on the wavelength. So the last problem is the airflow isentropically through a converging nozzle. At a section where the nozzle is 0.030 feet quadrat, the local pressure is 60 psi, the temperature is 40 Fahrenheit, and the Mach number is 0.52. The back pressure is 30 psi. Determine the Mach number at the throat, the mass flow rate, and the throat area. So my intention is, of course, to understand how to determine the Mach number at throat, the mass flow rate, and the throat area. Also, last but not least, to ask God to guide us to understand it better, how to solve this question. So first one is the initial thinking. For the initial thinking, we have A1 equal to A1 is 0.030 feet quadrat, P1 is 60 psi, T1 is 40 Fahrenheit, and we convert it to Reaumur, which we get 499.6. So the Mach number at point 1 is 0.52. The T is throat. P at throat is 30 psi, and lambda is 1.4. It is for air. Here we get the R is 1760 feet times lbf per slug L. It is gas constant for L, and we get here the free body diagram. So the water enter from the first area to the second area. So the second area is the throat actually. So next, I'm sorry, I forgot. For this problem, we use the isentropic flow equation, which is T0 per T1 equal to 1 plus lambda min minus 1 per 2 times M1, Mach number at point 1 quadrat, and the P0 per P1 equal to open bracket T0 per T1 close bracket lambda per lambda minus 1. So the idealization of this problem is that we assume that the system is isentropic, the flow is subsonic. So the subsonic mean there will be no shock wave in the flow to modify the flow stagnation, and the flow is choke. So the Mach number at throat is 1. So next is instruction. So for the instruction is first we have to find the T0. So to find the T0 we use the equation T0 per T1 equal to 1 plus lambda minus 1 per 2 times m1 quadrat. So we get the T0 per T1 is 1.054 and the T0 we get 526.65 R. So after we find the T0, we find the P0 with the equation P0 per P1 equal to open bracket T0 per T1 close bracket pangkat lambda per lambda minus 1. So we got P0 per P1 is 1.2 psi. So for the P0 is 72 psa. So because at the throat of a converging nozzle Mach number is equal to 1, so the isentropic relation to find fluids at throat, we have to find the T throat using the first equation, but we at the Mach number we use Mach number at throat which is 1, and we get the T0 per T1 is 1.2 R. So we arrange the equation and we so that the T throat equal to T0 per T1. So the T1 we get that we change the T1 to T0 per T1 and we get that T throat is 348.8 R. So after that we use the same method to the P throat and we get the P throat is 38 psa. So after next so after we find the T throat and P throat, we have to find the mass flow rate. So we use the equation m dot equal to P1 times A1 times M1 per root T1 times root lambda per R times open bracket 1 plus lambda minus 1 per 2 M Mach number at point 1 quadrat close bracket pangkat minus lambda plus 1 per 2 open bracket lambda minus 1 close bracket. So I use the scientific calculator, so we get the m dot is 0.050 lbm per s. So after we find it, we find A at throat. So we use the equation of m dot equal to P1 A throat per root T throat times root A per R. So we rearrange the equation and we get the A throat equal to m dot times root T throat per P throat times root lambda per R. So we get the A throat is 0.258 feet quadrat. So the conclusion is we get the Mach number at throat is 1, we get the mass flow rate or m dot is 0.050 lbm per s second, and we get the area at throat is 0.258 feet quadrat. So that is for my presentation about my final exam. If you have any question, you can write it down in the comment section below and we can discuss it together so we can get more understanding about fluid dynamics. Okay, thank you so much for your attention. Wassalamualaikum warahmatullahi wabarakatuh.